Alright, hello everyone, welcome to another video on machine learning. In the last video, we were talking about one classification algorithm. It was the k nearest neighbor algorithm, which we studied with a few examples, right? And in this video, we are going to look at another classification algorithm. It is called naive Bayes classification. So this is going to be based on the Bayes theorem that is given to us by this guy that you see on your screen, Thomas Bayes. So he is the man for our video. So without further ado, let us begin the video. Let us begin by talking about the definition of naive Bayes. It is a classifier, alright, that comes from a family of simple probabilistic classifier. So there is going to be some notion of probability that we are going to use, and this notion of probability is going to come through the application of Bayes theorem. Alright, and then there is going to be a strong independent assumption between the features. Alright, so we are going to assume that the features are independent. What this means is that I am going to have, say, 3 features and 1 target. Alright, say this is my data set with features x1, x2, x3 and target y. Alright, so my assumption is that my target is going to depend on the feature. That is fine. Okay, my features are going to influence what my target is going to be. But my features are not going to influence one another. So one feature is not going to depend on another feature. Okay. Once again, what does this mean? This independence means that my features are not correlated. Okay. Now, had my features been correlated, then I could have used some algorithm that takes advantages of the fact that my features are correlated. But in naive Bayes, I am not going to take any advantage, right? So I am not going to, even if my features are correlated, this correlations advantage will not be taken off in naive Bayes. So naive Bayes is simply going to assume that the features are not correlated. There is no relation among all these different features. There is relation between the target and the feature. Yes, my feature are individually going to influence the target, but one feature is not going to influence another feature, right? So there is a strong assumption that there is a strong independence among the feature. All right, and because of this assumption, because of the assumption that the features are not related to one, are not dependent on one another. All right, because of this assumption, our algorithm that we are going to develop in this class, all right, this naive Bayes algorithm that we are going to see, this is going to be easy. Okay, so implementation of this algorithm, derivation of this algorithm, to think about this algorithm, all these are going to be easy. All right, why? Because of this assumption that the features are independent. So because the algorithm is simple, okay, it is called naive Bayes. The word naive means simple. Okay. Now, once again, to recall the terminology, these are features, also called independent variables. Okay, the value of these variables are not dependent on anything. This is target. These are the dependent variables. Okay, the value of this target depends on the features, on the independent variables individually. All right, so all of them, they influence the target, but there is no relation among all these different features. All right, this assumption is the most important takeaway from this particular slide, that there is a strong independence assumption between the features. All right. Now let us talk a little bit about how probability. So we said naive Bayes is going to be a probabilistic classifier. So let us talk about how probability can be used. Okay, we are not going to go too deep into mathematics right now. First, let us try to visually build an intuition of how probability might be used. Alright, to do classification. So here I have a data set where I have abdomen length and antenna length of grasshopper and clatidids. Alright, for example, this is a data point corresponding to one particular grasshopper which had a uh, antenna length of 5.5 and abdomen length of 2.5 centimeter. Alright, there is another grasshopper with abdomen length, antenna length equal to 3 and abdomen length equal to 1. Here is a data point corresponding to a clatidid that had a uh, antenna length of 9 and a abdomen length of 8. Alright, so in this way I have a data set. Alright, and this is my complete data set. Okay, with several grasshopper given to us by this blue circle and several clatidids given to us by this red squares. Alright, so let us go ahead and do a few things uh, with this data set. What we are going to do first is we are going to convert whatever data we have into a histogram. Alright, so this is the histogram. Now I am taking only one feature, that is antenna length. This other feature that I have had, abdomen length, I am going to ignore that at this moment. So let us work with only one feature for ease of understanding. Okay, so I have antenna length and I am going to bin this into different uh, groups and I'm going to simply do the count. Okay, here I have say 1, so this is equal to 1. Okay, here I have say 2 very data points, so 2 clatidids. Here I have 4 clatidids, so I have 4 clatidids, red corresponding to clatidid and blue is corresponding to grasshopper over here. In this point I can see I have uh, 1 clatidid and 3 grasshopper. Alright, so yeah, this is what the histogram means. Histogram is just giving me the count. Another thing that you should note is that my number, the axis in this histogram, this x-axis, it goes like this. 1 is here, 2 is here, 3 is here, 10 is over here. Okay, so this is how the histogram is moving, right? So you can see in this graph below, my 1 is here and that corresponds to this region. Okay, my 10 is here and that corresponds to this region. I simply rotated this in this direction. I took the histogram, that this image that is in this manner, and I rotate it like this, right? So this comes to this direction, and yeah, this is what it is. The axis goes from 1 in the right hand side to 10 in the left hand side. Normally what happens is in real number line I have 1 in the left hand side and 10 in the right hand side. Alright, so this is normal, but this is what we have. Alright, so yeah, next what we are going to do is we are going to create normal curve out of this histogram. So we are going to draw these two curves that you see below on your screen. We are going to create these two curves that fits this histogram. So you can see that the curve looks like the histogram. Alright. So right now we are doing everything visually. We don't need to create histograms in order to draw this kind of normal curve. We simply need to go through the data set, find the mean and the uh, standard deviation or covariance. That would have given us hold on. Alright, sorry for the interruption. Uh, we could have found the mean and standard deviation or variance, and that would have given us the normal curve directly. But here, just for ease of visualization, first we are creating this histogram and then we are fitting this normal curve. Alright, so this is what we have. Now we are going to use this normal curve. What is the normal curve? This gives us the probability distribution. Normal curve gives us the Gaussian distribution, right? So this curve is giving us the probability distribution. We are going to use probability. So let us go ahead and use this normal curve to make a classification. Now I am given a insect with antenna length equal to 3. I am told that there is an insect with antenna length equal to 3, and I am asked what is the insect. What I am going to do is I am going to come up to 3. This is 1, this is 2, this is 3. I am going to come up to 3, and I am going to see, I am going to draw a perpendicular line, and I am going to see where the line intersects with my curve, okay, with my normal distribution. And so I am going to do that. I see that my line, this at 3, at antenna length equal to 3, if I draw a perpendicular line, it intersects the red normal curve, it corresponding to clatidids, it intersects that at 2, and the blue curve that corresponds to grasshopper, it intersects that at 10. So I am going to use that to make this probabilistic prediction. Okay, so what is the probability of uh, the insect being grasshopper given that antenna length is equal to 3? This is something that I have to answer, and I have to answer what is the probability that the insect is a clatidid given that antenna length is equal to 3. Okay, this is something else that I have to answer. Now from my curve, I see it intersects the clatidid curve at 2, and it intersects the grasshopper curve at 10. Okay, so 10 and 2 is the value I get from this normal curve. Normal curve, this you might have guessed by now, this has an amplitude. Okay, forget if you did not understand what having an amplitude means, but this is what I get from the normal curve, right? Now the probability of grasshopper and the probability of clatidid, okay, these two are the only option that I have. So the probability of grasshopper plus the probability of clatidid should be equal to 100% or 1. But here I see when I add the probability of grasshopper and the probability of clatidid, I am getting 12. Okay, so 12 is not something that I am interested in. 12 does not make any sense when I have total probability as 12. Okay, total probability should be 1. So what do? I am going to normalize it by the total sum. So 10 plus 2. This is what I am going to divide this with. 10 plus 2. So this is what I have. This is going to give me 10 by 12, and 10 by 12 is equal to, hold on, uh, 10 divided by 12, this is going to give me 83 0.83. Alright, and this is going to be 2 divided by 12, and that is going to be 0.17. Alright, so this is what I have. Now I am going to say that given that the antenna length is equal to 3, the probability that the insect is a grasshopper, okay, the probability of grasshopper given that antenna length is equal to 3 is equal to 83%, and the probability that the insect is a clatidid given that the antenna length is 3 is equal to 17%. So I have the probability of this insect with antenna length 3 being a grasshopper, that probability is 83%. This is much higher than the probability of clatidid, which is 17%. So the classification that I am going to do, okay, is going to be, I am going to say that the insect is a grasshopper. Alright, so this is using probability. This is how we use probability to do classification. Alright, let's do this again. I have another measurement, another insect with a antenna length of 7. Okay, now I have to find probability of grasshopper given antenna length equal to 7 and probability of clatidid given antenna length equal to 7. I go to this curve. I see my at 7. I intersect with the uh, grasshopper curve at 3. Okay, and I intersect with the clatidid curve at 9. So 3 plus 9 is 12. Once again, not equal to uh, uh, this is not equal to 1. Okay, probability should be equal to 1 or 100%. This is definitely not equal to 1. So let us normalize this and make this equal to 1. I am going to divide by 3 plus 9. Once again, I am going to divide by 12. So 3 divided by 12 is going to give me 0.25, and 9 divided by 12 is going to give me 0.75. So I am going to say that the given antenna length equal to 7, the probability that the insect is a grasshopper is 0.25, and given antenna length equal to 7, the probability that the insect is a clatydid is 0.75 or 75%. Now I am 75% sure that the insect is a clatydid, and I am 25% sure that the insect is a grasshopper. So the classification that I am going to do is I am going to say that the insect is a clatydid. Alright, okay, let's do this again. Here I have an insect whose antenna length is equal to 5. Is this a grasshopper or is this a clatydid? Let us try to figure out. Probability of grasshopper given antenna length equal to 5, and probability of clatydid given antenna length equal to 5. So I see at 5, okay, these two curves are intersecting. Okay, at this point the two curves are intersecting. Alright, so that is the exact point where I am trying to find the value that this curve is giving me. Okay, so I see both this blue curve and red curve, they are intersecting at this point, and the value is equal to 6. Okay, so I have both equal to 6. 6 plus 6 once again is not equal to 1. So my total probability has to be 1. So I normalize it and I get this is equal to 0.5 and this is equal to 0.5. So right now I am 50% sure that my insect is a grasshopper, and I am 50% sure that my insect is a clatydid. So now I have a dilemma. Okay, now if someone asks me to classify, I am not sure anymore. Alright, so this is what I have. So yeah, a little bit of confusion. So pointing out that this kind of confusion may also exist. Now before going any further, one out of today's topic thing that I want to say. Okay, had this been my data set, instead of using all this probability and all this thing, there is something else that I could have done. Okay, I could have simply drawn a line like this, okay, that separates these two classes very properly, and then what I would have done is I could have said that if my data point is above this line, then say that the insect is a clatydid. If the data point unknown data is below this line, then say that my insect is a grasshopper. So I could have drawn a line like this to do this classification, and that is something that we are going to do in another video. Today's video we are going to use probability. Okay, so this part, forget about what I said regarding line, and let's move on with probability. Okay, now I'm going to give away two data points. Okay, it says 90% of librarians are shy and introvert, and 5% of farmers are shy and introvert. So somebody probably did this study, okay, and he found that 90% of librarians are shy and introvert, and 5% of farmers are shy and introvert. Okay, so it so happens that you meet a shy and introvert guy on your way to college. All right, so now here is the question: what do you think is this guy? Is this guy a librarian or is this guy a farmer? So it's definitely a classification problem, binary classification. You have to say whether this guy is a librarian or this guy is a farmer. Alright, so classification problem. You are given this data that 90% of librarians are shy and introvert, 5% farmers shy and introvert. So what is the probability with which you are going to say this person is a librarian or this person is a farmer? All right, so yeah, you are probably, or I am probably going to say that this shy and introvert guy that I met on my way to college is a librarian, because most of the librarians are shy and introvert. So let us think about this thing mathematically. Say there are 100 librarians. Okay, say there are 100 librarians in total. 90 of them are shy and introvert according to this statistic. and say there are 100 farmers in total. 5 of them are going to be shy and introvert. So out of these 200 people in total, 95 of them are shy and introvert. Alright. So out of 200 people, 95 of them are shy and introvert. You meet a shy and introvert guy. What is this, a librarian or a farmer? So let's try to figure that out. Okay. What is the probability that the person is a librarian given that the person is shy and introvert? Okay, so 95 people are shy and introvert. Out of that, 90 are librarian. So this is equal to 0.945, I believe. Okay, so do this calculation, figure out what is the value. Alright, and the probability of that person being a farmer given that the person is shy and introvert is equal to 5 out of 95. So out of this 95 shy and introvert guy, 5 of them are farmer. So out of 95, 5. So this 5 by 95 is the probability that the shy and introvert guy is a farmer. Okay, so this is going to be 0.054. Okay, maybe. All right. So yeah, now if someone asks me, is this guy, this shy and introvert guy, is this a librarian or a farmer? I'm going to say that I'm 94%, 94.5% sure that this guy is a librarian, and I am 5.4% sure that the guy is a farmer. So yeah, I am probably going to say that this shy and introvert guy is a librarian. Okay, this is what I make this classification. I do this classification given only no other data, right? It's only given this data. Okay, fine. Now I'm going to show you how prior knowledge changes our calculation. Okay, what is the prior knowledge that I'm going to give you? The number of librarians and the number of farmers. Say in India there are 1 lakh librarian and there are 10 crore farmers. Alright, now everything is going to change. If there are 1 lakh librarian and 10 crore farmer, okay, yeah, 90% of librarians are shy and introvert. So how many shy and introvert guys, librarians are there? There are 90,000 shy and introvert librarians. There are 10 crore farmers. How many shy and introvert farmers are there? There are 50 lakh shy and introvert farmers. Alright, so this is what I have. Okay, this is 5,000k, I believe. Okay, let me write it down. 50 lakh, 50,000,310. Okay, this is 500k, 5 lakh, 5, yeah, 5,000. Okay, and this is equal to 9 into 10 to the power 4 shy and introvert farmer, and 500 into 10 to the power 4 shy, sorry, 9 into 10 to the power 4 shy and introvert librarians, and 500 into 10 to the power 4 shy and introvert farmers. Alright, so yeah, now our calculation is going to change a lot. Okay, now you can see there are 90,000 uh, shy and introvert librarians. Okay, there are 1 lakh librarians in total. Out of this, 90% of them are shy and introvert. So there are 90,000 shy and introvert librarians. Fine. Only 5% of farmers are shy and introvert compared to 90% of librarians. Only 5% of farmers are shy and introvert. But there are 10 crore farmers. Alright. So 5% of 10 crore is equal to 50 lakh. So now you see, now you have 90,000 uh, shy and introvert uh, librarian and 50 lakh shy and introvert farmer. So what is the total shy and introvert guy? Count. Total shy and introvert is equal to 50 lakh 90,000. Okay. Uh, Population. So there are 50 lakh 90,000 people who are shy and introvert. So what is the probability of this shy and introvert guy being a librarian? So probability of librarian given that the person is shy and introvert is now there are 90,000 shy and introvert guy, shy and introvert librarian out of total shy and introvert people in the world 50 lakh 90,000. Okay, so the probability boils down to 9 divided by 509 is equal to 0.0176 or 177. Okay, and the probability of that person being a farmer given that the person is shy and introvert is equal to how many farmers are there? uh, 500 into 10 to the power 4 divided by 509 into 10 to the power 4, and this is going to be equal to 0.983 I believe. Okay. 500 divided by 509 is yes 0.9, okay sorry, 0.9823. Alright. Now see, after this new knowledge, after this knowledge about the population, okay, the demographic, how many farmers are there, how many librarians are there, after this new knowledge is given to me, I am 98.23% sure that this new shy and introvert guy is a farmer, and I am only 1.7% sure that the person, this shy and introvert guy, is a librarian. Okay, although 90% of librarians are shy and introvert, and only 5% are uh, of farmers are shy and introvert, but there are so many farmers compared to librarians that if I meet any random shy and introvert guy, it is almost sure that the person is a farmer, okay, not a librarian. This is because the number of farmer is so large compared to number of librarian. So a large percentage of librarian is still smaller than a small percentage of farmers. Okay, a small percentage of farmer is also a very big number. Okay, you see this. So what is the takeaway from this slide? See, I was doing a calculation. I was almost sure, but then I got some new knowledge, some prior knowledge that helps me to scale things. Alright. And because of this prior knowledge, now my calculation has entirely changed. Okay, some previous knowledge is given to me that changes my calculation rapidly, all right, dynamically. So this is what is the takeaway. Prior knowledge is going to change our calculation. Okay, this is the Bayes theorem. All right, the equation of Bayes theorem. It says that if there are two events, okay, one dependent on the other, so the probability of A happening given that B has already happened is equal to probability of B happening given that A has happened into probability of A divided by probability of B. Alright, this is the prior, this is the evidence, and this is called likelihood, this is called posterior. Alright, these are just terminologies, but this is what it is. If you need visual demonstration, graphical explanation with animation and everything of why bias theory is true, you should, once again, I am going to recommend a channel that I have been recommending in this course for a very long time, 3 brown 1 blue. Okay, that channel has a very beautiful video with animation demonstrating why bias theorem is true. Go through that video. Alright, and anyway, you must have studied bias theorem back in school with explanation, so I'm not going to go into explanation again. Alright, yeah, this is what I have. There are two events, A and B. What is the probability that A is going to happen given that B has happened? This uh, this has happened. B has happened. What is probability that this will happen? Okay. So given that B has happened, what is the probability that A is going to happen? That is what Bayes' theorem gives us. Now, of course, this means that there is a relation between A and B. Okay. Given that B has happened, that changes the calculation of A. Otherwise, what is the probability of A? That is this prior. Okay. But then, because of this relation between A and B, uh, things are going to change. Now, how does this fit into Naïve bias classifier? We are going to see that very soon. But one thing that I want to tell you right now is there is a relation between our target and each feature, right? Each feature is going to influence our target. So our target is dependent on the probability of our target. Okay, the probability of the class of this classification that we are trying to do is dependent on the uh, probability of the feature. All right, but the features do not depend on one another. All right, so this is going to give us somehow, later on we will see how this is going to give us what is the probability of something given that what is the probability of a target given that some feature configuration is there, given some unknown data, what is the probability of the class. All right, so that is what we are going to do. But before we do that, let us solve one problem with Bayes theorem. Okay, simple problem. A doctor has found that COVID causes fever 50% of the time. Okay, so probability of uh, fever given that the person has COVID is equal to 0.5. All right. Uh, these are not real data. Okay, these are synthetic data. These are data. These are just random numbers that I put over here. So don't take this as medical advice. If you have fever, go to doctor, get tested. Okay. So a doctor found that COVID causes fever 50% of the time. Further, he found that 1 in 50,000 people are infected by COVID. So what is the probability of COVID? 1 in 50,000. Okay, that is 0.2 into 10 to the power minus 4. Alright, and 1 in 20 people have fever. Okay, what is the probability of fever? 1 in 20. That is 0.05. Alright, so this is what we have. Okay, doctor found that COVID causes fever. If I have fever, if I have COVID, then what is the probability of fever? 50%, 0.5. He found that 1 in 50,000 people are infected by COVID. So probability of COVID 1 by 50,000. He found that 20% have 1 out of 20 people have fever. So what is the probability of fever? 1 by 20. Alright. Now here is the question. If I have fever, okay, what is the probability that I have COVID? Okay, what is given? Given is I have fever. This event has occurred. I have fever. Now what am I trying to find? What is the probability that I have COVID? So let us try to find that. Given that I have fever, what is the probability that I have COVID given that I have fever? Bayes' theorem is going to give us probability of fever given COVID into probability of COVID divided by probability of fever. Alright, and this is equal to 0.5. Okay, this is equal to 0.5. I get it from here. This is equal to 0.2 into 10 to the power minus 4. This I get from here, and the denominator is probability of fever. This is equal to 0.05. If I solve this, I am going to get 0.0002. Alright, so this is equal to 0.02%. So if this is the data, then given that I have fever, what is the probability that I have COVID? It is 0.02%. Alright, so this is what I have. If I have fever, then there is only a 0.02% chance that I have coronavirus. Okay, this data is synthetic. Once again, do not take this as medical fact. Okay, this is not medical fact. This is not scientific fact. These are numbers, just random numbers that I put on your screen to do calculation. All right. If you have fever, please go to a doctor and get tested for COVID. Okay. Uh, So I had to say that if someone takes this as scientific fact, have fever, and then uh, later on realizes that person has COVID, and that is going to be bad. So anyway, let's move on and look at this. This is the data set. All right, and ultimately in machine learning we are going to do everything on data set. Okay, and this is the data set that we have. What are the features in this data set? I have only one feature. What is the color? Okay, and I have only one target. I am of course going to have only one target, and what that is fruit. Okay, so given the color of a fruit, I have to tell what is the fruit. Okay, is it an apple or is it a mango? There is one more column, serial number. This is something that is not going to influence my data analysis, and so I ignore this. Alright, so one feature, one target. Feature is the color of the fruit, and fruit columns gives me the name of the fruit. Alright, for example, this tells me that there is a apple which is red, there is a mango which is red, then I have a apple red, another red apple, a green apple, another red apple, a green mango, another green mango, a red mango, and yet another green mango. Alright, so these are the fruits that are there in my data set, and from this now I have to answer this question. Given a green fruit, is it an apple or a mango? Okay, so in probabilistic notation, what am I being asked? What is the probability of the fruit being an apple given that the fruit is green? Okay, so that is something that I have to find out. Probability of the fruit being an apple given that the fruit is green, and I have to find out what is the probability that the fruit is a mango given that the fruit is green. Alright, so let's go ahead and try to solve this. So Bayes' theorem is going to give us that probability of the fruit being apple given that the fruit is green is equal to probability of the fruit being green given that the fruit is apple, and probability of apple divided by probability of green. Okay, Similarly, for a probability of mango given the probability of green, I am going to first find out what is probability of the fruit being green given that the fruit is mango. Then what is the probability of mango divided by probability of green. Alright. Now all these different components I have to figure out before I can answer, calculate this, right? So let us try to figure out all these different components. Alright. So first I have to figure out what is the probability of apple and what is the probability of mango. Okay. So let's look at the fruit column. Okay. This has apple and mango. So let's look at this column. Okay. On this target column. Okay. So there are 10 uh, rows in my data set. Okay, there are 10 items in my data set. Out of these 10 items, I see 1, 2, 3, 4, and 5. Okay, sorry. Yeah, hold on. 1, 2, 3, 4, 5. These 5 of them are apple. So out of 10, I have 5 apples. So my probability of the fruit being an apple is 0.5. That is 5 out of 10. Okay, out of 10 total fruits that I have, 5 of them are apple. Alright. What is the probability of the fruit being a mango? 1, 2, 3, 4, 5. So once again, 5 out of the 10 fruits are mangoes. Alright. So these are the probability of apple and probability of mango. Now let us try to figure out what is the probability of red and probability of green. Okay, so 1, 2, 3, 4, 5, 6. 6 out of these 10 data points that I have, 6 of them are red, right? Out of 10, 6 of these fruits are red. So there is a 60% probability that my fruit is red. The probability of red is 60%, and therefore there are 1, 2, 3, 4. 4 fruits that are green. So out of 10, 4 are green. So there is a 40% probability that my fruit is green. Alright. Now, what is the next thing that I have to find? I have to find probability of green given apple. Okay. This is the thing that I need to find. So let us try to find out how many apple are there. This is an apple. These are all apples. Okay, so I am going to consider these are the data points where apple is given, right? I am trying to find the probability of green given that apple. These are the data points corresponding to data points given that it is an apple. These are apples. Okay, and I am going to find the probability of green given that the fruit is an apple. Okay, so these are all the fruits that are apples. Alright, so among all these apples, what is the probability that the fruit is green? Okay, so I have red, 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 green, red. So I have 5 apples. Okay, 4 of them are red, 1 is green. So 1 out of 5 is green. So probability of green given that the fruit is an apple is 0.2. Alright. Similarly, I can find what is the probability of green given that the fruit is mango. Alright, probability of green given that fruit is mango. So this is the mango and these are mangoes. Okay, so this is a red mango, a green mango, red mango, and green mango. So I have 5 mangoes, 2 of them are red and 3 of them are green. So probability of green given that the fruit is mango is 3 out of 5, and that is equal to 0.6. Alright, now I have all the data that I need to find probability of the fruit being an apple given that the fruit is green. Okay, so what is the probability that the fruit is green given that it is apple? I have found that it is equal to 0.2. Okay, then what is the probability of the fruit being an apple? Okay, apple and mango in my case are equal. I have equal number of apple and mangoes in the world. Okay, so it is 0.5. I have said something very important. I have used this word in the world. I'm going to talk about that soon. Okay. Then what is the probability of green? Probability of green I have found is 0.4. Okay. If I do this calculation, I am going to find this is equal to 0.25. Alright. Now, what did I figure out? I figured out that the probability of apple given that the fruit is green. Okay, given that the fruit is green, what is the probability that the fruit is an apple? There is only a 25% probability that the fruit is an apple. Okay, so that would mean there is going to be a 75% probability that the fruit is a mango, because probably given that the fruit is green, the probability of it being an apple and the probability of it being a mango together, they should give me 100% probability, right? There is only two kind of fruit in our universe, apple and mango. But let us calculate that. Okay, using this formula, I know it is going to be 75, 0.75, but let us still go ahead and calculate that. So probability of green given mango is equal to 0.6. Probability of mango is equal to 0.5, and probability of green is equal to 0.4. Okay, and this is equal to 0.75. Alright, so this is what I have. Okay, uh, so given a green fruit, hold on. Okay. Given a green fruit, is it an apple or a mango? I am 25% sure that it is an apple, and I am 75% sure that it is a mango. So, given a green fruit, I am going to probably classify, I am probably going to guess that the fruit is a mango. Okay. Yeah. So, this is what I have. Let us verify this number. I found that probability of apple is given that the fruit is green is equal to 25%, and probability of mango given apple is fruit is green is 75%. Let us verify that. How am I going to verify that? So this is a green fruit, these are two green fruits, and this is a green fruit, right? So I have four green fruits. All right, and I see out of these four green fruits, one of them is apple and three of them are mango. Okay, therefore out of all these four green fruit, uh, only 25% of them is apple, right? uh, and 75% of them are mangoes. So that aligns with what we have figured out through calculation. Alright, so yeah, what we have done, we have applied naive bias. Alright, I am finding it difficult to say naive bias over here. Why? Because I have only one feature, and naive bias assumes that there is no correlation, okay, between different features. But here I have only one feature, and so there is no question of the features being independent, of there being correlation between different features. Anyway, this is the technique of using Bayes theorem to do classification. Alright, and that is what we have done. Yeah, one thing that I said to you in passing, but I did not uh, talk about this in detail, is this. And what I'm going to say next is going to be true regardless of the algorithm. Okay, right now we are doing naive Bayes algorithm, but uh, any algorithm that we use in machine learning and statistics assumes that the data set that you have, okay, is representative of the true population. Okay, your data set is going to be only sample data. Okay, you do not have all the information about everything, right? You have only sample data. Now, for example, say in Jorhat, I want to figure out how are all the students, what are all the students studying, what is the distribution of all the students studies, all right, all the college student studies is how many people are studying, what is the percentage of people studying engineering, what is the percentage of people studying general studies, what is the percent studying medicine. So this is something that I want to figure out. All right, so there are say 10,000 students in Jorhat, and I send someone to collect sample. Okay, so that person is going to, if that person comes to JEC, okay, and he asks 100 people, what do you study? Okay, everyone is going to say, in Jorhat Engineering College, everyone is going to say, I study engineering. So this person has created a data set where everybody is saying that they have studied engineering. So if I use this data set to do an analysis of the students of Jorhat, I will end up analyzing that all the 10,000 students of Jorhat are studying engineering, right? Because my data set is not representative of the true fact of Jorhat. Now, say there are 100 students in Jorhat, 100 students in JEC, 200 in JB College, 300 in Medical College. If this happens, all right, then this person who was collecting the data, what he should have done is he should have come to JEC and randomly sampled, say, one person, two people from JB College, three people from Medical College. So that would have been representative of the true ratio of students, right? So my data set need to be representative of the world, okay, of the total population. So if I have found in my data set that 50% of the fruits are apple and 50% of the fruits are mangoes, then really in the uh, all over the world 50% of the fruit should be apple, 50% should be mango. Okay, it should not be that in my sample, in my data set, I have 50% apple and 50% mango, but in the real world there are 70% of the fruits are mangoes and 30% of the fruits are apple. If that happens in the, that is the fact in real world, and I have something else in my data set, my data set cannot be used to do prediction in the real world. Okay, once again, this says that 60% of the fruits are red and 40% of the fruits are green. So this is what I get from the data set. My data set should be randomly sampled from the real world, and uh, if these are true, then even in real world, 60% of the fruit should be red and 40% should be green. Okay, but this is just sample data set that I created on my own. Okay, this is not through some rigorous scientific study. Alright, so this is what I have. This is very important. Okay, not only in this Naïve bias, but in any algorithm, my data set that I use to make prediction about the world, okay, should be representative of the world. Okay, we don't say world, we say population. This sample data should be representative of the population data. Okay, more technical terminology. So this is what I have. Alright, this is how I have answered this question. Given a green fruit, is it an apple or a mango? Alright, so far so good. Really easy things that we have been doing till now. Let us increase the complexity a little bit. Let us increase the number of features. Okay, now I am looking at a data set that has 4 features and 1 target. So these are the features, and this is target. Alright, so this is my data set, and you have seen this data set before. You have seen this data set in the last class. This is the play tennis data set. In the last class I asked you to do one homework wherein you had to do a one hot encoding of this categorical data set to convert it into a numerical data set, and using that numerical data set and Hamming distance, you have to find distance from a unknown data and to do prediction using k and n. Okay, using Hamming distance and after doing one hot encoding. That was the question given to you in the last class. In this class we are going to use the same data set to do prediction of this unknown data, given that given this unknown data, I have to predict whether this person is going to play tennis or this person is not going to play tennis. Alright, so what I am going to do is this. I am going to find probability that the person will play tennis. Yes. Given this data, what is the data? Rainy, hot, high. That means outlook is rainy, temperature is hot, humidity is high, and wind is false. Alright, so I am going to figure out what is this probability, and I am going to figure out what is this probability. Okay, so these are the two probabilities that I am going to find. Probability that the person is going to play given this data, and the probability that the person is not going to play given this data. Okay. In the next few slides, instead of writing this very long thing, I may simply write data. Okay, that this is equal to this. All right. So this is just a short form. Don't get confused. This is not something else. When I write data, it simply means that I am shortening this into this thing. All right. So to find probability of yes given data, I have to find probability of data given yes into probability of yes divided by probability of data. Alright, and in the same way we will find probability of no given data is equal to probability of data given no, probability of no, and probability of data. Alright, so these are what we have. Okay, so we have to do all this calculation. So before doing this calculation, there is a small thing that I want to talk about. This is the difference between independent and dependent events. So our features are independent, right? So what does that mean? Okay, let us say uh, there are bags of marbles. Okay, so there are 5 marbles in a bag, and there is another bag with same 5 marbles. Okay, two of these marble are red and three of them are green in this bag. In this bag also two of these marbles are red, three of them are green. So you can see that the two bags are same in configuration. Now what do we have to do? First I put my hand in one bag and pull out a marble. Then I put my hand in another bag and pull out a marble. So my question is this: what is the probability of A and B happening? Where A is I pick red marble and B is I pick another red marble, say again red marble. Okay, so this is the question that is given to me. What is the probability that I pick a red marble from bag 1, and even B is what is the probability that I pick a red marble from bag 2. Okay, so what is the joint probability that I have to answer? What is the probability that I pick a red marble from bag 1 and a red marble from bag 2? So I have to pick red marble from both these bags. Alright, now here is a question that I want to ask beforehand. So this is bag 1, okay, and this is bag 2. Okay, so here is my question. Uh, uh, is me picking a marble from bag 1 going to influence what I pick from bag 2? That means if I pick a red marble from bag 1, is it going to influence my probability of picking a red marble from bag 2? No, right? Both of these are independent events. So we are talking about independent events right now. Okay, both of these are independent events. What is going to happen if both of these are independent events? Let us try to use this tree diagram method that we used in combinatorics in discrete maths. Okay, first event is picking from bag 1. There are 5 possibilities. There are 5 marbles, so I can pick one of these 5 marbles. 2 of them are red, 3 of them are green. Alright, then after picking from bag 1, I am going to pick from bag 2. So after I might have picked the first red marble, and then how many options do I have? I have 5 options again. Okay, from bag 2. This is picking from bag 1. This is pick from bag 2. Okay, so once again 5 option, 5 option. Alright, so this is picking red again. These are green, 2 red, 3 green, and these are red, green. Okay, red, red, green, green, green. So how many outcomes do I have in total? I have this 5 plus this 5, this 5, 5, 5. So I have 25 outcomes that are possible in total. Okay, out of this 25, this corresponds to picking a red in the bag 1, red in from bag 2, red from bag 1 and red from bag 2. This corresponds to red from bag 1 and red from bag 2, red from bag 1 and red from bag 2. Everything else, this corresponds to picking green from bag 1. Okay, and it does not really matter what I pick from bag 2, right? Because I have picked a green from bag 1. Okay, so these are not events of my interest. I have 4 events of my interest. Out of all these 25 events, 4 are of my interest. That is, I pick a red from bag 1 and I pick a red from bag 2. So what is happening? In this place, okay, up to this point, these are the 2 events. There are 5 events possible. Out of these 5 events, 2 of them are of my interest, right? So 2 out of 5 is the one that I choose. Okay. Now after choosing this 2 out of 5, I ignore all the other events, the other 3 out of 5. I ignore them. Out of this 2, 5, how many of are my interests? So each of these 2 by 5 is going to give me 2 by 5 events. There are 5 more events for each of these 2 out of 5 events that are going to be of my interest, right? So yeah, there were 5 events originally, that is speaking from bag 1. Out of this 5, 2 were of my interest. Now of these 2, after these 2, I am going to have 5 events each, 5 events each for each of these 2, and out of those 5 also, I have 2 events which are of my interest, right? So for each this 2 event in bag 1, I have 2 event in bag 2, that are of my interest, and I multiply them, I get 4 out of 25. Alright, so this is how I get this 4 out of 25. How? What I could have done, say I have some probability of picking from bag A, bag 1, say that is PA, and I have some probability of picking a rate from bag 2, say P of B. Okay, so probability of A and B is probability of A multiplied by probability of B. Okay, so this is what I have. Say now I make some change in my requirement. I say event A is I pick red marble from bag 1, event B is I pick green marble from bag 2. Okay, now what is going to happen? So all these events of picking green marble from bag 1 is not of my interest. Okay, so there were 3 events which are not of my interest. These are 2 events of my interest. Here I am picking a red again. Here I am picking a red again, not of my interest. Here I am picking a green after picking a red from bag 1. Here I am picking a green. Here, 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 and here. These are 6 events out of these 25 possible events. Okay, this rest of the 15 events I am not showing. Okay, so these 6 events are of my interest, right? So 6 out of 25, and I could have arrived at that using this. What is the probability of A? What is A? I pick a green marble from bag 1. There are 5 marbles in sorry, I pick a red marble from bag 1. There are 5 marbles in bag 1, 2 of them are red, so probability of A is 2 out of 5. What is probability of B? B is I pick a green marble from bag 2. So probability of B is 3 out of 5. Okay. So what is the probability of A and B? That is, I pick a red marble from bag 1 and a green marble from bag 2. Probability of A and B is 2 by 5 into 3 by 5, and this is equal to 6 by 5. Yes, we get this from formula, and we can verify this using the tree method. Alright. So this is what I have. Alright, this is the case in case of uh, independent events. The 2 events, me picking a marble from bag 1 and me picking a marble from bag 2, they are not dependent on one another. Alright. So in case of 2 events A and B which are independent, the joint probability of A and B, both A and B happening, is the multiplication of the probability of A and the probability of B. Alright, so this is the formula in case of independent events. Now let us talk about dependent event. Okay, so probability of picking a red, probability of picking a green. I will soon formulate the problem, but let us first say what is the probability of picking a red. Okay, in the first try, given this bag, I have one bag B, that this bag has 5 marbles, 3 of them are green, 2 of them are red. So what is the probability that I pick a red? So out of 5 marbles, 2 of them are red. So 2 out of 5, okay, 0.4. This is the probability that I am going to pick a red. Okay, what is the probability that I am going to pick a green? So I am going to pick either green or red. So both this probability is going to add up and give me 1. So 1 minus 0.4. 0.4 is the probability of red. So probability of green must be 0.6. Alright. Anyway, the probability of green is 0.6 because there are 5 marbles and 3 of them are green. So 3 by 5 is equal to 0.6. Alright, this is the probability of me picking a red marble or a green marble, uh, that is 0.4 and 0.6, given this kind of a bag. Okay, in the first try. Now here is the thing, I am given 2 events A. pick first and pick again. Now this is the same bag. Once I pick a red, okay, then my probability of picking a red again is going to change, right? Let us understand this. If I pick a red first, then probability of picking a green, given that I have picked a red first, is something, and probability of picking a red, given that I have picked a red first, is something. So probability of picking a red was 4% in the first try. Okay, uh, first time I picked, it was 40%. Now what is the probability of picking a red? Okay, there were 5 marbles in total. 2 of them were red. I picked a red. How many are remaining? There are 4 marbles remaining. Okay, one of them is red. There were 2 reds. I picked one red remains. There were 3 green, they were as it is. Now I have 4 marbles in my bag. 3 of them are green, 1 of them is red. So what is the probability of green? The probability of green is 3 by 4. 4 marbles, 3 green. Okay, so 3 by 4 is the probability of green. This is 0.75. What is the probability of red? There are 4 marbles remaining, 1 of them is red. So 1 by 4. Okay, this is equal to 0.25. See, things have changed. This was my initial probability. After I made one action, okay, my second probability has changed. This was not the case in case of independent event. Here my second event, what is the probability? Okay, this is dependent on first event. Say instead of picking red first, if I pick green first, then what is the situation going to be? Picking green, given I picked green first, the probability is going to be, there are going to be 4 marbles remaining. uh, 2 of them are going to be green, 2 of them are going to be red, so this is going to be 50%. Alright, probability of red, given that I had picked a green first, this is also going to be 50%. Alright, so see, the probability of whether I am going to pick a green or a red. Okay, what is the probability of me picking a red in the second time is going to change depending on what I picked on the first time. So this event of picking marble, okay, 2 marbles, first and second, they are dependent on one another. Okay, the probability of my second trial is going to uh, change depending on what I did in the first trial. Now say I have to find the joint probability. Okay, probability of A and B, where A is I pick red and B is I pick red again. Okay, so probability, what is the probability of I pick red? The probability of I pick red at first attempt is 0.4. Okay, then what is the probability of I pick red again? Given that I have picked red, okay, the probability of me picking red again is equal to uh, 0.25. So this is 0.4 into 0.25, and that is going to give me a total probability of 0.1. That is, now I have a 10% probability that I will pick 2 red continuously. Okay, there is 0.1% probability. Now again let us do this. Probability of A given B is probability of, see, B is the second event that depends on the outcome of first event. Alright, so what is the first event? I pick red. Second event I pick green. So probability of first event 0.4. Probability of second event, that is I pick green given that I have picked red, is equal to 0.75, and this is equal to 0.3. There is a 30% chance that I am going to pick a red first and then a green. Okay, so that even happening, the probability is 30%. Alright, so to formulate this we have done the calculation. Let me write down the general formula. Probability of A given and B happening. Well, B, the probability of B happening depends on what is the outcome of A. This is equal to probability of B given A into probability of A. This is the formula in case of dependent events. Alright, so why is all this necessary? So why did I teach you all these things? Alright, hold on 1 second. Almost done erasing the board. Alright, I'm done erasing the board. Alright, so in the last slide we were trying to do something. Hold on 1 second. In the last slide, sorry for the interruption, this was the unknown data, right? So to these are the things that I have to find. Okay, so to find this I need my data is equal to rainy, hot, high and false. Alright. So this is my data. And what are the things that I have to find? I have to find probability of data. This comes in the denominator. Alright. This value and this value. And I have to find this as well. This one and this one. Alright. So I have to find probability of data given some class. Alright. Now this data, it contains of 4 independent features, right? This feature has some values: so rainy, hot, high and false. So I have 4 different features and these are all independent. So this event, the outlook being rainy, the probability of the temperature being hot, the probability of humidity being high, the probability of windy being false, all this we assumed are independent. Alright. So the probability of rainy is not going to be dependent on the probability of the temperature being hot. Alright, that is the assumption that we make. In reality, this independence is really not going to hold, whether all this weather data is dependent on one another, but then let us assume uh, there is no dependency. Okay, let us assume they are independent. So all these are independent event. So what I can do is I can multiply all this probability, right? So probability of rainy, hot, high and false is equal to probability of rainy into probability of hot, probability of high into probability of false. Alright, so this is the equation that I have. Then what is the probability of the data given that I have some class? Okay, this given that I have some class. Okay, given that I am going to play tennis. Alright, so say these are the data, these are the data that corresponds to me, this guy playing tennis. Alright, now what is the probability of that the temperature is that the outlook is rainy given that he is going to play uh, tennis? Is it dependent on what is the humidity that he is playing tennis, or what is the temperature that he is playing tennis, or what is the wind situation like given that he is playing tennis? Alright, these features were independent anyway. Okay, so given the outcome, these features are still going to be independent, right? So this probability of the data, okay, the joint probability given this class is going to be probability of rainy given class. Alright, probability of uh, hot given class into probability of high given class into probability of false given class. So this class in our case can be either yes or no. So I have two classes, no and yes. Right? So in our case, these are the two classes. Uh, so yeah, that is what we have. In general, if I have say feature 1 up to feature m, then the joint probability is going to be the multiplication of all these individual features. Probability of feature 1 into probability of feature 2 up to probability of feature m, and the probability, joint probability of these features given some class is going to be probability of feature 1 given class into probability of feature 2 given class, so on, probability of feature m given class. Alright, this is the general formula. Alright, and this is what we are going to use. Now we have to figure out things like what is the probability of rainy, what is the probability of hot, what is probability of high, what is probability of rainy given yes, what is probability of rainy given no, what is probability of hot given yes, what is hot probability of hot given no. So all these things we need to figure out. So that is what we are going to do in this next slide. Alright. So the data set is there as it is, and then we have a table. Okay, this table is going to be there in our RAM. Okay, and it is going to be there as a two-dimensional array. That means each of the cell I can go to that cell in constant time. Okay, and I can do addition multiplication in constant time. So yeah, this is what I have. Now I am going to fill the cell. Okay, so say all these cells are filled with 0. Okay, all these values are 0. What do I have? I have a few tables, in fact. Okay, this is my table corresponding to feature 1, this is my table corresponding to feature 2, this is table corresponding to feature 3, and this is table corresponding to feature 4. Okay, these are the 4 features, and these are the 4 tables corresponding to these 4 features. What do I have? Along the column I have the different classes, so I have two classes here, no and yes. So along the columns I have yes and no. Okay, so two classes throughout, right? In all the tables I have these two classes along the columns. Along the rows, what do I have? I have see, this is the table corresponding to outlook. So outlook has sunny, overcast and rainy. So the possible value of outlook is what I have along the rows. Alright. Similarly, in case of temperature, temperature may be hot, mild or cool. So I have hot, mild or cool. Alright. Windy can be high, normal. I have high and normal. And sorry, humidity is high and normal. Windy is true or false. So I have true and false. Alright, so this is what I have. Alright. Now initially say all of my tables are filled with zeros. Right. All these are say filled with 0. Right. So let us imagine that. Now what I am going to do is as I go through this uh, data set, okay, I will go through this data set row by row, and as I go through this data set I am going to keep on filling this table. So how do I keep on filling this table? This is what I do. I see outlook is sunny and play tennis is no, right? So I am going to go into this outlook table. I am going to go into this sunny uh, row and then this no column, right? So target is no, therefore I am going to go into this no column, and outlook is sunny, so I am going to go into sunny row, and then I am going to increment that by 1. All right. So this is what I do. Then I go into the next feature, temperature. Temperature is hot, plate in is still no, so I go into no column of temperature, hot row of temperature, I increment that by 1. Okay, humidity is high, I increment no humidity row, no column by 1. Windy is false, so I go to false column of windy and no, uh, sorry, false row of windy and no column, and I increment that by 1. Okay, so this is how I have done processing row 1. Okay, then I come to row 2. This is sunny, outlook is sunny, and play tennis is no, so I go to row sunny no, and I increment by 1. Okay, so I had 1, now I have 2. I see hot and no, so I go to temperature. Now I am looking at temperature column, so I go to temperature table. There is this hot and then this no. I had 1, I increment this uh, again. Okay, then high and no, I go to high, I go to no, there was 1, I increment this to 2. Then there is windy and true. Now I go to true row, and in windy table I go to true row and no column, and I increment that by 1. Alright, I am done with row 2. Now I go to row 3. In row 3 I look at outlook, it says overcast, so I go to overcast row, and outlook plateliness is yes, so I go to yes column, and I increment that by 1. Alright, hot and yes, I go to hot and yes, I increment that by 1. There is high humidity and yes, so I go to high and yes, I increment that by 1. Windy is false and plateliness is yes, so I go to false and I go to yes. Okay, this particular column I increment that by 1. Alright, so I hope you have understood how to fill up this column. Alright, now I am going to do this a bit quickly. Alright, so this is done. Next, this is rainy, so I go to rainy, increment, sorry, this is yes, this is rainy is done. Mild, I go to mild, increment, high, I go to high, increment, false, I go to false, increment. Okay, this row is done. Next I go to rainy, and there is yes, so rainy, I increment, cool, I increment, normal, I increment, false, I increment. Alright, next is this row, rainy and this no, so I will now go through this no column. Alright, uh, rainy, increment to 1, right, cool, I increment to 1, normal, I increment to 1, true, I increment 1. Alright, then I go to this overcast, and this is yes, so I will manipulate this column, okay, corresponding to yes. So what I'm going to do, overcast I am incrementing by 1 to up to 2. So cool I am incrementing by 1, normal I am incrementing by 1, and true I am incrementing by 1. Okay, okay, sorry, I made a mistake. True I am incrementing by 1, not false. Okay, then to this row, sunny, it is no. So now I will work on this no's column. Okay, so sunny I am incrementing by 1, mild by 1, high by 1, false by to this row. It says yes, sunny incrementing by 1, cool and incrementing normal, I'm incrementing false, I'm incrementing. Okay, again this is yes, so rainy, I'm incrementing mild, I increment normal, I increment and false, I increment. Alright, then this sunny, this is once again yes, sunny, I increment mild, I'm incrementing normal, incremented, true, incremented. This is yes again. Overcast, I have incremented mild, I have incremented high, I have incremented true, incremented. Right. Then yes again. Overcast, incremented, hot, incremented, normal, incremented, false, incremented. Right, now I have no. I will work in this column, no's column. Rainy, I am incrementing mild, I am incrementing high, I am incrementing, and true I am incrementing. Alright, so let me clean up all the clutter. I have 2 over here, I have 4 here, 3 here. Alright, so these things that I have cut away, let me remove all those. Alright, so this is what I have. Okay, this is how I have filled the table. Now one more thing that is left to do is this: how many yes are there and how many no's were there. Now in this data set I can see there is 1 2 3 4 5 6 7 8 9 9 yes, and there are 1 2 3 4 5 no's. Alright, so I have 9 yes and 5 no. So what is the probability of yes and what is the probability of no? There are 14 data points in total. Out of this 9 are yes. So 9 out of 14 is the probability of yes. There are 14 data points, out of this 5 are no. So 5 out of 14 is the probability of no. Alright, now if I sum up over here, 3 4 5 6 7 8 9, I have 9 yes, 5 no. Alright, in temperature also I am going to have 9 yes, 5 no. Everywhere I am going to have 9 yes, 5 no, and 9 yes, 5 no. Okay, this is going to be true throughout for every table. You just take some time to figure out why this is going to be true, because this is the target, right? Uh, whatever be the feature that you take, uh, 5 of them are going to be false and 9 of them are going to be true. Alright, so this is going to be true throughout. Now here is the question. I am trying to find, my unknown data set was rainy. hot, high, and false. Alright, this was my unknown data set, and I have to find things like what is the probability of raining given yes, what is the probability of raining given no, right, what is the probability of hot temperature given yes, probability of hot given no. So let us figure it out. Uh, there are 9 days, 9 years, right? There are 9 days when I played tennis. All right. Uh, we are looking at Outlook right now. So there are 9 days in total when I played tennis. Out of these 14 days, I played tennis for 9 days, and out of these 9 days, what is the probability that it is raining? All right. So 3 days out of these 9 days, it rained, right? So the probability that it is raining is 3 out of 9, right? Out of these 9 days, 2 days were sunny. Right. Out of these 9 days when I played, okay, so given that I have played, what is the probability that it is sunny? So given that I have played for 9 days. So out of these 9 days, how many days were sunny? 2 days were sunny. So 2 out of 9 is the probability of sunny given that I have played, given yes. Alright. Similarly, overcast is 4/9. Okay. Now, what is the probability that the days was sunny given that the person did not play? So, the person did not play for 5 days, right? For 5 days, the person did not play. Out of these 5 days, 3 days were sunny and 2 days were rainy, right? So, given that the person did not play, what is the probability that the day is sunny and what is the probability that the day is rainy? So, given that the person did not pay for 5 days, okay. Given that the person did not play, how many days he did not play? 5 days. Out of these 5 days, 3 days were sunny. So, what is the probability of sunny given that the person did not play? The probability is 3 out of 5. So, out of 5 days, he did not play. Out of 5 days, he did not play. That he did not play. 3 days were sunny. So it is 3 out of 5. Then overcast is 0 out of 5. Then rainy is 2 out of 5. Right. So from this table, by filling up this table, what did we figure out? We figured out what is the probability of rainy given yes. The probability of rainy given yes is 3/9. What is the probability of rainy given no? The probability of rainy given no is 2/5. So 3/9, 2/5. Then what is the probability of hot given yes? So let us fill this for the temperature. Okay. So out of all these 9 days that he played, okay, now I am trying to figure out what is the probability that the temperature is hot given that the person has played tennis. Okay, so out of all these 9 days that the person has played, 2 of these days were hot. So 2 out of 9 is the probability that the day was hot given that the person has played tennis. Alright, 4 out of 9 is the probability that the day was mild, and 3 out of 9 is the probability that the day was cool. Similarly, 2 out of 5 is the probability that the day was hot given that the person did not play tennis. Alright. 2 out of 5 is the probability that the person that the day was mild given that the person did not play tennis, and 1 out of the 5 is the probability that the day was cool given that the person did not play tennis. Alright, so this is what I have. So what is the probability of hot given yes? What is the probability that the temperature is hot given that the person has played tennis? So it is 2/9. Okay. What is the probability that the temperature is hot given that the person did not play tennis? 2/5. Alright, we are not done. We have to find probability of high given yes, probability of high means high humidity given yes, high humidity given no, probability of windy being false, given yes, and probability of windy being false given no. Alright, so this is going to be uh, probability of high given yes is 3 by 9, probability of normal given yes is 6 by 9, probability of humidity being high given a person did not play tennis is 4 by 5, probability humidity is normal given person did not play tennis is 1 by 5. Alright, then let's work with windy. Probability that it was windy given that the person has played tennis is 3 by 9. Probability that it was not windy given that the person played tennis is 6 by 9. Alright. Similarly, probability that the day is windy given person did not play tennis is 3 by 5, and probability that day is not windy given person did not play tennis is 2 by 5. Alright, so probability of high given yes is 3 by 9, probability of high given no is 4 by 5. So let's write that 3 by 9, 4 by 5. Probability of false given yes is 6 by 9, probability of false given no is 2 by 5. This is what I have. Alright, now a few more things that we need to figure out. Okay. These are, yeah, let's figure those things out over here. Okay, what is the probability of sunny, probability of sorry, I don't need the probability of sunny. Okay, I need probability of outlook being rainy, temperature being hot, humidity being high, and windy being false. So rainy, I see in the outlook column. Okay, there are 14 different data points over here. Alright. So out of these 14, how many rainy is there? There is 1, 2, 3, 4, 5. So probability of rainy is 5 out of 14. Alright. Then what is the probability of hot? So temperature being hot, 1, 2, 3, 4. So 4 out of this 14, the temperature is hot. What is the probability of the humidity being high? Alright. So 1, 2, 3, 4, 5, 6, 7. 7 out of 14 is the probability of humidity being high. See, this is not having any condition, right? This is without condition. I am not asking you what is the probability that the temperature is probability of high given yes. Okay. And what is the probability of windy given what is the probability of windy? Sorry, what is the probability of false? Windy being false. So I have 1, 2, 3, 4, 5, 6, 7, 8. 8 out of 14 is windy. Right? So these are the data that we have. Now let us try to calculate the probabilities. Alright. So probability of yes given this data is equal to, we have already formulated the equation. It is going to be probability of data given yes into probability of yes divided by probability of data. Okay, and this is equal to this. I am going to now split into the individual component. Alright, so this is probability of rainy given yes, probability of hot given yes, probability of high given yes, probability of false given yes. Okay, so probability of data given yes is now split into the individual component, and this finally I have to multiply into probability of yes. Okay, and this denominator is probability of rainy into probability of high hot into probability of high into probability of false. Okay, so this is going to be 3 by 9 into 2 by 9 into 6 by 9 into 3 by 9 is probability of rainy given hot, 2 by rainy given yes, probability of hot given yes is 2 by 9, probability of high given yes is 3 by 9, and probability of false given yes is 6 by 9. So these are what I have: 3 by 9 into 2 by 9 into 3 by 9 into 6 by 9, and probability of yes is equal to 9 by 14. Okay, so this is what we figured out, and this is what I'm going to write: 9 by 14. This is my numerator. In denominator I am going to have 5 by 14 into 4 by 14 into 7 by 14 into 8 by 14. Alright, so my numerator is going to be 0.010582. I had already calculated this beforehand, so I'm not going to calculate that. I have to calculate the denominator, so please bear with me. It is 5 divided by 14 into 4 divided by 14 into 0.5, 7 divided by 14 into 8 divided by 14. Made some mistake. How do I edit this equation? Do I have to write everything again? It is stupid. Please bear with me. This I believe is equal to 0.0 29154. Alright. So yeah, this is what I have, and this is equal to 0.01052 divided by 0.02915. This is equal to 0.363. Alright, next let us try to figure out the probability of no given data. So data is of course this. So this is equal to probability of rainy given no into probability of hot given no into probability of high given no into probability of false given no into probability of no divided by probability of rainy to probability of hot into probability of high into probability of false. Alright, so the numerator is going to be 0.018286, and the denominator is going to stay the same, right? The denominator did not change, and this is the important thing, that the fact that the denominator did not change is going to be important. We are going to talk about that soon. Okay, denominator is 0.29154. So let me do this division. This is going to be what previous equation turned out to be 0.363. So this is going to be 1 minus 0.363, right? But let us still calculate. This is 0.363. 0.0188286 divided by 0.029154, and this is going to be 0.627. Alright, so this is what we got. Probability of yes given data, this unknown data, is equal to, we figured out that is equal to 0.363, and probability of no given the unknown data is equal to 0.627. So together these two adds up to 1. Okay, so yeah, I see that there is a 62.7% probability that the person is not going to play tennis given this weather condition, and there is a 36.3% probability that the person is going to play tennis given this unknown weather condition. Alright, so given that the probability of not playing tennis is higher, I am going to classify that the person is not going to play tennis. Alright, so this is what I am going to do. Alright, so yeah, this is what I have. Now, one thing that I want to point out, okay, are we really interested in figuring out the probability? Alright, so that is something that we have to decide. If my application needs probability value, then I have to figure out the probability value precisely. This is what we did, have been doing till now. Uh, this is what the formula is, base formula to find out probability. Okay, but do I really need to find out exact probability using this base formula? No. Why not? I am interested simply in doing the classification. Alright. In order to do this classification, I just need uh, to know which of these different classes is going to have the higher value, is going to have the higher probability. I do not need to figure out the exact probability. I just need to know which of these, say this, there are two classes in this example, which of these two classes is going to have the higher probability. Alright, now the denominator is multiplication of probability, numerator is multiplication of probability. Probability is always uh, non-negative. Okay, in fact, it is going to be a positive number, non-zero even. So all of these are going to be positive number, both numerator and denominator. All right. So the denominator is going to be the same for all the classes. All right. No matter how many classes I have. Here I have two classes, yes and no. Even if I had more classes, the numerator, this is called the evidence in Bayes formula. Okay, is probability of data. Okay, so probability of this thing. So this is going to stay the same in all my equation. Okay, I have two equations here. Equation 1, equation 2. The denominator of these two equations are the same. So even if I had more than two classes, I would have had more than two equations. The denominator of all these more than two equations would have been the same. So that would have given me the probability. Right. Now here is the thing. I am the numerator, the equation whose numerator had the highest value would have been the highest probability, right? So we are dividing all this number by the same denominator, right? So the highest number is ultimately going to end up being the highest probability. The bigger the number, after dividing, say I have two numbers 4 and 2, I divide by 2, so 4 is bigger than 2, my answer after dividing is going to be 2 and 1, so 4 becomes 2 and 2 becomes 1. The one that is bigger, 4, it ends up being bigger even after division, right? So this inequality is going to stay, is going to hold even after division. So if I am just simply interested in uh, doing this, if I am simply interested in classification and I do not need the exact probability, then I can simply calculate the numerator, the class, the equation that will have the biggest numerator is going to be my class, right? If I don't want to find the exact probability. Anyway, the one that has the biggest numerator is going to have the highest probability. That is going to be true because all these different numerators of all these different equation, we are anyway going to divide by the same denominator. So we can avoid doing this. Okay, that will simplify our calculation without changing our classification. Our classification, whatever classification we would have made, we are going to make that anyway. So that does not change anything. Alright. So in the next example that we are going to see, we are not going to do this division by denominator. Alright, and I hope you understood why dividing by denominator is not necessary. Anyway, the things that we have done till now, it is Naïve Bayes. Okay, this is the Naïve Bayes classifier algorithm. Alright, so essentially I need to fill a table. Once I have filled a table, it is going to take means everything is going to be very fast, right? Now one point to note, how much time do I need to go to one cell of this table and then increment the value of that cell? I need constant time. Okay, how much time do I need in total to fill this table? Okay, I have to go through each of the row only once, right? And I have to go through each of the feature on my data set. Each of these things I am going to through this only once. So if I have m number of features and n number of rows, then for each row I have to do m number of calculation. I have to, for each of these m feature, I have to go once to the table and increment one value. Alright, so this is one constant operation per cell of the data table. There are m cell in one row, so each row is going to take order of m amount of time. Okay, is each row, and there are n number of rows, so in total I need n into m uh, time to fill this table. Okay, once I fill this table, I have to do I have to go through this table again. I have to divide all these things that are in the yes column by the number of things that are in the number of yes. Okay, and all the things that are in y column using this by 9. So I have to go through this again, through this table again. Okay, if there are if there are how many rows, there are k number of rows and k number of classes and p number of rows, then this is also going to take order of k into p. Okay, so yeah, many people may know what kp is. Okay, so this is what I have. Alright, anyway, this table is going to be far smaller than my data set. Okay, so this is going to dominate the entire time, and this is going to be insignificant. Alright, uh, so yeah, this is what I have. This is the time complexity of this algorithm. And one thing that is good about this algorithm is we go through this data set only once. Okay, there are algorithms that you are going to see very soon called gradient descent that will go through the data set iteratively. It will go through this data set over and over again. Okay, but in Naïve bias we don't need to do that. We go through this data set only once. Even in regression algorithms that we saw till now, we go through data set only once, right? So this is an advantage of Naïve bias. It is very fast, all right? And once we have created this table, calculating all this probability is very fast, right? So we just simply look up for each of this value. We look up in the table. So the if there are m number of features, then calculating each of this probability is going to take order of m amount of time. So we are going to do m plus 1 multiplication in the numerator, m multiplication in denominator, and 1 division. So order of m. Alright. So yeah, this is what I have. A very fast and good algorithm. Alright. So this is Naïve bias classifier. Now up to this point we had been working on a data set that is categorical. Okay, so we found this discrete probability by counting through this data table. We have been counting. Okay, how what is the total number of even, what is the total number of yes out of all this total yes, how many total rainy is there. Okay, how what is the total number of no out of all this no, how many total rainy is there. So we did this by counting in this categorical data set. Next, let us look at another data set. This is a numerical data set. Okay, so here I have the height of a person, here I have the weight of a person, and here I have the foot size of a person, and finally I have the target. This is the gender of the person. Alright, so these height are in feet. So one thing that has been done is this feet is 5 feet 11 inch. Alright, this has been converted into decimal value. This is a bizarre, feet inch is bizarre. Okay, I don't know why people use this kind of things. So anyway, feet, what is the problem? These inches go up to 11, then it rolls over up to 0. So two digit decimal number, it should have gone from 0 up to 0.99. Okay, then it would have rolled over to the next value. Again, it would have become 0. But this is a mod 12 kind of thing. Okay, at least the inch is mod 12, feet is in some other infinitely going in one direction. This is very problematic. Okay, so we have converted this into normal decimal form. What did we do? What did we do? We took this 5 and then this 11 by 12. and this becomes 5.92. Okay, this is how we converted this feet into numericals, means decimal normal numbers. 5 feet 7 inch became 5 7 by 12, and this is equal to 5.58. so this is how we have converted this feet and inch into these numbers. Alright, so this is one point. Okay, now here is the demo. Say I have this. Okay, this is the column, and I am given what is the this is my unknown data, right? The height is 6 feet, the weight is 140 pound, and the foot size is 8. Okay, this is the data that is given to me. uh, Say I have to make a prediction of what is the probability of weight equal to 140. Okay, so exact probability is not something that we are going to find here. Okay, since it is continuous, there are lots of theories behind this. We will not go into those. So exact probability of 140 is going to be 0. All right, but we are going to see around that area around 140 what is the probability. So we are going to use something called probability density function. Okay, PDF. So continuous probability density function, and this is given to us by Gaussian distribution. A Gaussian distribution is defined by two things: the mean and the standard deviation. Okay, so I say I am interested in finding the probability of weight being 140. What I am going to do is first I am going to find the mean of weight. So say mu weight is the mean of weight, and standard deviation of weight, say sigma weight is the standard deviation of weight. Okay, so I am not going to use the standard deviation directly. I am going to do the square. So this is going to be variance. Square of standard deviation is variance. Anyway, when you are going to calculate, first you have to calculate the variance, and then you take a square root, that is going to give you standard deviation. No need to take the square root, you end up with variance, so you will have the variance. So we need to calculate the variance of weight and the mean of weight. So yeah, so given this mean and variance of weight, I can do this. I can use this formula. This is the probability density formula, uh, 2 pi sigma square. Okay, uh, e to the power, there is going to be a minus before, x minus mu whole square to sigma square. Alright, so this is the formula. Alright, where sigma square is this variance, sigma is the standard deviation, sigma square is the variance. So sigma square, I am directly going to replace this with variance, and mu is the mean. Okay, so we have to calculate from here, and we will find the mu and the sigma square. Okay, uh, by doing, I will add up all this thing, and that is going to give me the mean, and variance is I am going to go through all these rows. I am going to find the difference from the mean. I am going to square that. I am going to add them up, and so mean and variance, both of them I will divide by the total number of rows in my data set. So I should not really explain what is mean and variance. I have done that before. Okay, so this is what it is. Okay, this is how I am going to find mean and variance, and then I will put this mean and variance in this formula. This x is going to be 140. Okay, so I will put 140 in place of this probability. I'm trying to find probability of 140. So I will put x equal to 140. Mu will be equal to the mean, and sigma square is going to be the variance. So these are things that I'm going to figure out. I will place them in this formula, and then it is going to give me some value, and that is going to be my probability of uh, weight being 140. Okay, so yeah, this is what we have. But then I am not interested in finding weight, probability of weight being 140. Okay, I am interested in finding the probability of weight being 140 given that the person is, say, male. Okay, now what I am going to do, I will take only those rows, okay, which has my target as male. Alright, these rows do not have target as male, so I am going to remove these. So only those rows that have my target as male, I am going to take those rows, and from those rows only I am going to figure out what is the mean and what is the standard deviation, variance. Alright, so these two are the things that I am going to figure out, but I am going to now, I am trying to find weight, probability of weight being 140 given that the person is male. Okay, so I will take only those rows which has male. Okay, so this is what I do. I take mean, and I take sigma square. Alright, and I place them in this equation, and this is going to give me the probability of weight being 140 given that the person is male. Alright, this is what I have. Alright, so what do I need to figure out? I need to figure out the probability, the mean and variance given that the person is male. Mean and variance given, mean and variance of height given that the person is male. Mean and variance of height given person is female. And similarly, mean and variance of weight for both male and female. Mean and variance of foot size for given both male and female. So let us go ahead and find that. Alright, this table contains all this data. I have height, weight, and foot size. Alright, so three different uh, uh, features that we have, and then for each of the feature given whether for male, what is the mean and variance. This is the mean, this is the variance for male. Given male, what is the mean and variance of weight. This is the mean of weight, this is the variance of weight. What is the mean and variance of foot size. This is the mean, variance of foot size. Similarly, I have for female. Alright, mean of height for female, variance of height for female, mean of weight for female, variance of weight for female, mean of shoe size, variance of shoe size for female. So this is what we have figured out. Alright, done this calculation. Very easy to do this calculation, right? For example, to calculate this, okay, foot size of female, I am going to take only those rows that has female, alright, as the class, and then I will take this foot size given female. These are the number that I am interested in. I am going to add them up. So 6 plus 8 plus 7 plus 9. I am going to add them up, and I am going to divide by 4. This is going to give my 7.5. This is my mean. Okay, this is what I have, 7.5. Then how do I get this variance? Variance is going to be 6 minus 7.5 square. So I will take each and I will subtract by mean, and then I will take the square. So 8 minus 7.5 square, 7 minus 7.5 square, plus 9 minus 7.5 square divided by 4, and this is going to be equal to 1.67. Alright, so this is the variance. This is how I calculate the variance and mean of foot size given that the person is female. Alright, so this is what I do. Now let's go ahead and use this to do a prediction. Alright, so I am given this data. Alright, this is my probability density equation that I already showed. Okay, so what is the this is height, this is weight, and this is foot size, not width, this is weight. Alright, so this is what I have to put in the equation. The probability, this is probability density function, not exact probability. Okay, don't be surprised that I have some value greater than 1 over here. This is possible. That means the area under the curve has a value greater than 1. So that is entirely possible. Okay, means the area around 140 is height equal to 6. So in that region that I am looking at, I have a value, total sum value greater than 1. Okay, so yeah, what is the probability that the height is equal to 6 given that the person is male? I put the mean of height of male in mu. I put the variance of height of male in sigma square over here and here. Okay, I have sigma square at two places, so I put variance in these two places. Okay, variance is sigma square, sigma is standard deviation, so I am putting sigma square is equal to variance. So don't take variance square. Okay, so that would be standard deviation to the power 4. Okay, so if you have calculated standard deviation, take the square of standard deviation. If you have calculated variance, simply put variance. Sigma square is variance, so don't confuse that. Sigma square is not standard deviation. Okay, sigma is standard deviation. All right, so yeah, this is how I have put everything in this equation, and this x is equal to this 6, so I have put x equal to 6 in here, this mean in here, this is my variance, this is my variance. I have put all this thing, I calculate, I get this 1.579. Probability of weight being 140 given male is this. Probability of feet size being 8 given male is this. So I have done all this. Next, what do I need to do? I need to figure out this thing. What is the probability of male given that this is the data? Okay, so anyway my equation would have been probability of male given 6 148. This would have been probability of 6 148 given male into probability of male, okay, divided by probability of 6 148, and probability of female given 6 148 is probability of 6 148 given female, probability of female divided by probability of 6 148. Alright, so this is my equation, two equations. Alright, now this equation, both of this equation, you can see the denominator is same, so I am not going to use this denominator. Okay, anyway the one that has the higher numerator after division will have the higher probability, so I am simply interested in doing the classification. I don't worry about the exact probability, so I am not going to divide by the denominator to get the exact probability. Alright, so I'm ignoring this denominator. Alright, now this is what I need to calculate. Okay, so probability of 6 uh, this probability of 6 148 given male is equal to probability of 6 given male. Okay, probability of height being 6 given male, probability of weight being 140 given male, and probability of shoe size 8 given male. Right, this is the equation that we have from given the fact that all these columns, right, all these features are independent, right? So we can multiply this individual features, probability of individual features, to get the joint probability. All right, so this is what this thing is going to happen, become this part, this probability is going to become this. All right, and this is going to become this, right? So this I am getting from here, this I am getting from here, this I am getting from here. I have already calculated all these values. Alright, and what is the probability of male? Let us go back and look at this data set. This data set, I have 8 rows in my data set. 4 of them are male and 4 of them are female. Therefore, probability of male and probability of female is equal to, both equal to 4 by 8, that is equal to 0.5. Therefore, probability of male is 0.5. Alright, I do all this multiplication, I end up with this value. Alright, similarly for female, given this data, I will take all this mean and variance one by one, I will put into this equation, and that is how I will find out what is the probability of, say, height equal to 6 given that the person is female. Okay, so I will do all this calculation. I will find out this height equal to 6 given female, weight equal to 140 given female, feet size equal to 8 given female, and what is probability of female, once again 0.5. Rest I will get through this PDE, through this equation. Alright, and that is going to give me a value equal to this. Alright, so now I have calculated this numerator. At least I did not calculate the denominator, I did not calculate the exact probability, but I have calculated the numerator of the base formula. Okay, and whichever has the bigger numerator in base formula out of these two equation is going to have the bigger probability. Okay, so I see that the probability of given this features, this height being 6, weight being 140 pound, and shoe size being 8 inch, the probability of the person being a female is higher than the probability of the person being a male. Okay, at least the numerator of the for female is greater than the numerator for male, and because we are going to divide both of them by the same denominator, ultimately uh, the probability of this person given this data being a female is going to be higher than the probability of this person being a male. Alright, so this is what we are going to have. Therefore, we are going to classify, given this unknown data, we are going to say that the person is a female. That is what the classification is going to be. Alright, so this finishes all the examples for naive Bayes classifier algorithm. Let us review naive Bayes with a few points. It is simple and easy to implement, does not require too much training data. We have seen that it can handle both continuous and discrete data. It is highly scalable because it is fast. Alright, and because it is fast, it can be used to make real-time prediction. Prediction is really very fast. Okay, order of m. When training is order of m into m. Okay, both of them are relatively fast things to do. Alright, and this final point is something that I need to explain a little bit. Say I am trying to classify people based on eye color. Okay, whether this person is male or female based on eye color. Okay, so I am trying to classify like before with sorry, hold on. I am trying to find probability of that person being uh, male given. So now I have eye color brown. Height is say once again 6, weight is 140 pounds, shoe size is 8 like before, but now I have one more data. Okay, so this is the probability that I am trying to find, and another probability that I am trying to find is this probability of the person being a female given brown 6 148. Okay, this is another thing that I am trying to find. Now let us think about what is going to happen if this eye color is irrelevant. Okay, uh, then what is going to happen if say 20% of population has brown eyes, then if this is irrelevant, then 20% of male should have brown eyes and 20% of female should have brown eyes, right? If it so happens that 20% of male has brown eyes and 50% of female has brown eyes, then definitely uh, uh, eye color of eye is not irrelevant when trying to determine the gender of a person. All right, so if we assume that the color of eye is irrelevant, then both of them should have this equal value. Okay, so if 20% is the thing, right? I hope you get this, right? So if this data is irrelevant, then probability of brown given female should be almost equal to, even if not exactly equal to, but should be almost equal to probability of brown given male. Right? I hope this makes sense. Otherwise, if these are not equal, then if uh, these are not almost equal, then this data is not irrelevant. Okay. Now, if this data is irrelevant, then what is going to happen? Here, this equation is going to become probability of brown given male, okay, into probability of 6 given male into lots of other things. Similarly, this is going to become probability of brown given female into probability of 6 given female into lots of other things. Now see, I am multiplying both of these by the same value. Say this probability is equal to 0.2. So 20% of the people have brown eyes. So I am multiplying both of these by 2. So both of them are going to be multiplied by the same value, right? So this irrelevant feature is not going to affect my calculation. Alright. If I have say A and B and I multiply both of them by 2, then A and B still stays the same. Alright. So if I multiply if I have an irrelevant feature, both of them are going to have the same probability, and even if I take it, my calculation is not going to means whichever had the higher probability is going to have higher probability, whichever should have lower probability is going to have lower probability. Okay, so that is not going to change. So this is how Naïve bias is not sensitive to irrelevant feature. Alright, so this ends our today's class. So to do a simple revision, we started off by uh, having this introduction of what is Naïve bias. Then we looked at a data set which we visually uh, interpreted to figure out how probability fits into classification. Alright, then we talked about how prior knowledge can help us really change how we calculate probability. Then we talked about naive bias. We solved a problem with naive bias. Alright, then we used naive bias on a data set that had only one uh, feature. Alright, then we moved into then we moved into another data set that had multiple features to use this naive bias classifier to do classification. Alright, so yeah, that is what we did. So after working on this data set to do this classification, this data set was a categorical data set with discrete values. We moved on and did classification on a numerical data set, okay, where features are numerical. Anyway, my target is always going to be categorical because these are classification. In classification, my target cannot be numerical. That would be regression problem, right? So my target, don't worry about it, but my features are numerical. So that we did with numerical values and categorical values, right? So yeah, and then we did saw a few benefits of naive bias. So yeah, this is what we have. I hope you understood everything in today's class. If not, you are free to contact me through WhatsApp, uh, through call, or writing your doubt in the comment section below. Thank you for watching this video, and see you in the next video.